Thank you, Yifeng. Greetings, everyone. I thank the organizers, Jeff, Will, Greg, Freydun, and Takis for inviting me and for putting this meeting together. And I'd like to give a special thanks to the IPAM staff for making this happen despite the circumstances. It's very nice to participate. I'm going to tell you about the free boundary PDE and a related stochastic interacting particle system known as Brownian bees. Most of this is joint work with Julien Berestycki of Oxford, Éric Brunet of École Normale Supérieure in Paris, and Sarah Penington, University of Bath. And near the end, I'll also discuss some work with my former student, Aaron Beckman, who's now a postdoc at Concordia University. So the interacting particle system we consider is a special case of a branching Brownian motion with spatial selection, known as NBBM. The N refers to the fact that the number of particles is N, it's preserved for all time. This special case has been called the Brownian bees process. I'm told that Jeremy Questel suggested this name. He may be present, and perhaps later he can explain the history to us. In any case, it's an interacting particle system in RD, and they're N particles. They move as independent Brownian motions, and there's also branching. Each particle branches independently at rate 1, and when there's a branch event, there's a simultaneous selection event so that the total number of particles is preserved. I'll assume that the branching is binary, meaning that one particle splits into 2. And so at each branch event, another particle is removed from the ensemble. And the rule is that it's the particle that's farthest from the origin, which is removed. So the 3 pictures here represent the system at 3 different points in time. Initially, we have the particles diffusing in RD, and then at some time, one of the particles, say this particle highlighted in green, it tries to branch into 2 particles. Then the particle that's farthest from the origin, which is the one crossed out in red, this one is selected for removal. The circles here just indicate the radial distance from the origin, which is supposed to be here in the center. So this particle is removed, and then from the location of the green particle, 2 particles emerge, and they undergo independent Brownian motions, and the other particles continue, and then there's another branch event later, and the process continues like this. Okay. So because of the simultaneous branching and selection, the total number of particles is preserved. So the name Brownian bees is just because this gives the impression of a swarm of bees around the origin. Since the branching is, since the selection acts on the particle that's farthest away, this has a confining effect, as I'll explain. But this is a special case of NBBM in branching Brownian motion with spatial selection. One can formulate a more general model in this way. So there are N particles moving as Brownian motions. They branch independently at rate 1. On the branching event, you select the particle with minimal fitness, and that's determined by a fitness function, which I will use V to denote this fitness function. So this is a function of space. This has also been called the score function. So upon a branch event, you remove the one that has minimal fitness, so that there are always N particles in the system. I will use boldface X to denote the configuration at time t. So x1 to xn, these are the particle positions in RD. And the fitness of a particle is just V of x. So at the branching event, we remove the particle which has smallest value of V. You could think of this as a spatial Moran type model. There are different versions of this. One of the first versions, perhaps the first version of this, was due to Brunet, Derrida, Muller, and Meunier in 2006. As I've described it here, this version way of formulating it in terms of fitness function V and continuous diffusion is due to Nathaniel Berestycki and Li Zhao. So the fitness function has very interesting effects on the population. We're always selecting the least fit particle, and so that produces a kind of selection pressure that pushes the ensemble in the direction of higher fitness. In the picture here, the blue curves represent level sets of V. So if this green particle branches, if this is the ensemble, then the one minimal fitness is removed. Notice that the process really just depends on the geometry of the level sets of V and not on the particular values of V. So the process is unchanged if I were to replace V by f of V, where f is any increasing function, because that doesn't change the geometry of the level sets. So for the particular case that I will focus on, the Brownian Bees process, the fitness function is minus norm, Euclidean norm of x. So the particles tend to move toward regions of higher fitness, which means that they're always moving toward the origin, and we're selecting the one that's furthest from the origin. This has a confining effect on the population. A lot of interesting questions one could ask. Basically, we'd like to understand how the structure of V, fitness landscape, how that affects the evolution of the population. What's the behavior as t goes to infinity? How does the population move across the landscape? Is there a limit as n goes to infinity at fixed time? We'll call this a hydrodynamic limit, but as Nicolas pointed out in his talk, this has nothing to do with hydrodynamics, it's just the terminology. So does the empirical measure converge to a limit as n goes to infinity? Then I'd like to know whether these limits commute. Also, you could ask about the underlying branching process. How does the selection affect the genealogy of the ancestral process? I don't have answers to all of these, but I'll give some answers in the case of the Brownian Bees process. So there have been several other works, particularly in the case of one space dimension with a monotone fitness function, right? So suppose that we're in dimension 1 and the fitness function is just x, right? So it's increasing to the right. And in this case, since V is increasing in x, then we're always selecting the leftmost particle. In the selection process, the selection pressure induces a drift to the right. So here, although these are smooth curves, they represent paths of the Brownian motion. So at time t1, you have a branching event, the particle on the left is selected. At time t2, another branching event, the leftmost particle is removed, and so on. So instead of thinking about branching and selection, you could also think about this as a jump diffusion process, right? Instead of saying that a particle branches, you could say that at time t1, the leftmost particle jumps to the location of another particle randomly chosen from the ensemble. Okay? In time t2, similarly, there's a jump, and then they both diffuse. So from this perspective, it's clear, since the jumps only happen from the leftmost particle, that jumps are always to the right, and this will induce a kind of drift, an effective drift on the process. So it's known that for each fixed n, this selection pressure pushes the ensemble to the right with a positive speed. Namely, if you look at x, position of a particle, maybe the max or the min or any particle in between, it doesn't matter, x over t converges as t goes to infinity to a limit Cn, which is positive and deterministic. That's almost sure convergence. As n goes to infinity, it's known that Cn converges to 2. Although for finite n, the speed is not explicit. The error, that is the convergence to 2 in the n going to infinity limit, is quite large, meaning that this error goes to 0 rather slowly, like 1 over log n squared. This is due to these authors here. I believe the first one is in the case of discrete model, and the second case is for the continuous diffusion. For for those who know the topic, this is very reminiscent of results about stochastic Fisher KPP equation, where one considers the traveling waves for the KPP Fisher equation with a noise that is proportional to parameters, a sigma, and then there are expansions of the speed that show that the speed is less than 2 by an amount that's like 1 over logarithm of sigma. Okay, so a similar effect going on here. So there are also some outstanding conjectures about the genealogy of the process. It's conjectured that the ancestral process behaves like a Bolthausen-Stittmann coalescent on a certain time scale. The interesting feature of this coalescent process is that there are multiple simultaneous mergers in the family ancestry. So here we're thinking about the ancestry looking backward in time, family lines merge. And it's thought that this is due to the possibility of a single particle running very far ahead of the selection boundary and then quickly branching so that its offspring make up a significant fraction of the population. As far as I know, that conjecture is still open, but there's some progress that's been made regarding the timescale due to Pascal Maillard, also the Berestycki brothers, and Jason Schweinsberg. Again, this is for the one-dimensional case with monotone fitness. Also in that setting, it's known that there is a hydrodynamic limit. So this is recent work of Damasi, Ferrari, Prasuti, Sopranolotto. They proved a hydrodynamic limit for the empirical measure of the process. So this is a random probability measure on the real line. There's an atom at the position of each particle, weighted by 1 over n. And they proved that as n goes to infinity, for each positive time, the empirical measure converges to a measure which has density, v, which is related to a free boundary problem here. Global existence of a solution to this free boundary problem was proved by my co-authors Berestycki, Brunet, and Penington. So the free boundary problem involves a heat equation with a source. That's not surprising because we have diffusion, but then also the source comes from the fact that the particles are branching, there's a growth. And this equation for V holds only to the right of the interface, where x is larger than gamma. Gamma is the free boundary. That's the location where the selection is happening. At the boundary, V is equal to 0, and V is continuous with the boundary. There's also an integral constraint, which is natural because the measure mu is a probability measure for each n, and V also has total integral 1. Although this PDE is linear, the whole problem is nonlinear because of the coupling of V with the boundary through this integral constraint. If V moves too fast, if gamma moves too fast, then because of the Dirichlet condition, the total mass of V will decrease below 1. If gamma moves too slowly, then because of the growth, the total mass of V will increase. Instead of formulating that in terms of an integral condition, you can show that this is equivalent to the following, assuming V is twice differentiable at the boundary. This constraint implies that the flux through the boundary, derivative of V, is equal to 1 to preserve the total mass, and the free boundary velocity is proportional to the second derivative of V at the boundary, assuming that's finite. So it's interesting to compare that to the well-known Stefan problem, which also involves the heat equation. In that case, the flux condition, or the free boundary velocity, is proportional to the derivative of V rather than the second derivative. But like the so-called super cooled version of the Stefan problem, here the the free boundary is moving into the mass rather than away from it, as in the regular stiffened problem. So it's known that it's easy to check, that there are explicit traveling wave solutions to this free boundary problem. That is, there are solutions, there's a solution V bar, which is constant, has a constant profile within a reference frame moving with constant speed. So the traveling wave profile is just x e to minus x, and the speed is 2. Okay? So the traveling wave looks like this. Ahead of the interface, you have growth, but then the interface is moving at just the right speed so that the flux through the boundary offsets the growth, and the profile is fixed. So the 2 here is not surprising. Recall that as n goes to infinity, the speed of the finite n ensemble asymptotically is close to 2 and converges to 2 as n goes to infinity. Okay, so that's all in the one-dimensional case. Now let's think about the higher dimensional setting. For 2 or more dimensions, much less is known. The way I formulated the general NBBM process earlier, the fitness function was due to Nathaniel Berestycki, Zhao, and in addition to some analysis, they also did some nice numerical simulations. What I'm showing you here are 2 plots from their paper. On the left-hand side, they're showing what the particle system looks like at 5 different time points. And this is for a fitness function, which is just the modulus of x, the Euclidean norm of x. So in this case, the fitness increases away from the origin. And so particles tend to move away from the origin toward higher fitness. I think the initial condition here is that all the particles are at the origin. So at 5 later times, what you see is that the particles are clustered on these concentric rings moving outward. As time goes to infinity, they tend to choose a direction randomly and move in that direction, although there's some spread in the angle. So in the case of a linear fitness function, here v is just lambda.x. The particles tend to move in the direction lambda, and they estimated the width of the ensemble in the direction of lambda, and also the transverse width, as it depends on n. Okay, so our work has to do with this n-dimensional setting, and we're focusing on the case of fitness function that has compact level sets, namely the fitness function is minus Euclidean norm of x. So level sets are compact Euclidean balls centered at the origin, and the selection has a confining effect on the ensemble. And the results that I want to present are described by this diagram. In the upper left, we have the particle system, the NBBM process, and we prove that as n goes to infinity, the empirical measure for this particle system converges to a density which satisfies a free boundary problem. We prove global existence and uniqueness for the solution of the free boundary problem. We also prove that as t goes to infinity, the solution of the free boundary problem converges to a stationary solution, which I will denote by u bar, and this solves a certain eigenvalue problem. Going back to the particle system, if you fix n, so it's a stochastic system, the particles have a law, which is a probability measure on rd to the n. As t goes to infinity, the law of the particles converges to a stationary distribution exponentially fast. That is, this defines, in fact, it defines a positive recurrent Harris process on rd to the n. So there's a stationary distribution. Think of this as the large time limit of the particle system. Then as n goes to infinity, the stationary distribution converges in a certain sense to this object u bar, which satisfies the eigenvalue problem. That is, if you look at the density of particles in RD, that measure converges to the limit u bar. So in a sense, for this case, where the fitness function has compact level sets, the n to infinity and the t to infinity limits commute. All right. Let me spend some time explaining the results more precisely in aspects of the proof. So here's the hydrodynamic limit statement for d larger than or equal to 1 for the Brownian Bees model. Again, mu n is the empirical measure of the in-BBM process. Okay? So for each time, this is a random probability measure on RD. Let's also define a boundary process, MNT. So this is a stochastic process, and it's just the maximum Euclidean norm of a particle, okay, from 1 to n. So this process has jumps, but only downward jumps, because between the branch times, the particles x move as Brownian motion. So the maximum of their moduli is a continuous process. But at the jump times, the extremal particle, the one with maximum Euclidean norm, or least fitness, is removed, and so the maximum makes a discrete downward jump. All right, suppose we're given an initial measure, mu naught, so this is some Borel probability measure on RD. Let's assume that the initial particles, the in particles initially, are IID distributed according to mu naught. Then what we've proved is that for every positive time, mu n, the empirical measure, converges weakly, almost surely, to a measure which has density u, and the boundary process mn converges to a function r such that the pair ur solves a free boundary problem with this initial condition mu naught. So what is the free boundary problem? So the free boundary problem takes as input the initial measure mu naught, and the problem is to find a pair, the function u on Rd in time, and a radius function Rt, such that the following conditions hold. So u satisfies the PDE, heat equation, plus the source, and the domain is all points x and Rd, which are have magnitude less than Rt. So these are Euclidean balls of radius Rt, but then the radius is changing in time. The function u is required to be continuous for positive time, and take the value 0 on the boundary and beyond. Moreover, there's an integral constraint. The total mass of the density u is 1. So u is the density of a probability measure. The integral condition is satisfied in the sense that as time goes to 0, the density u converges weakly to a measure, the initial measure mu naught. So a result is that for any probability measure, any Borel probability measure mu naught, there's a unique global solution to this free boundary problem. Moreover, the boundary process, R of t, is finite for any positive time and actually continuous. It could be infinity initially, but as t goes to 0, Rt converges to the radius of the support of mu naught. Okay. All right, let me say a few things about the solutions. So although the domain in which the PDE is satisfied, these are Euclidean balls of changing radius, this is spherically symmetric. The solution u may not be spherically symmetric because the initial condition need not have spherical symmetry. If mu naught, the initial measure, has an atom on the edge of its support, then R of t must move outward very rapidly. Consider, for example, the case where the initial measure mu naught is a single atom, just a delta function at the origin, right? Then R0 is 0. But as for positive time, RT has to increase very rapidly, faster than square root of t, because if it did not, then the mass constraint could not be satisfied. Right? We know that the running maximum of the modulus of the Brownian motion behaves like square root of t, roughly, and so R of t has to move away from 0 faster than that in order that mass is not instantaneously killed. However, we can prove an upper Holder continuity bound for any alpha less than half. We can show that R of t satisfies an upper Holder bound of order alpha. R of t minus Rs is less than t minus s to the alpha for any s less than t. Okay. So this is natural considering the regularity of Brownian motion. If alpha is less than a half, then we know that Brownian motion is alpha Holder continuous. If alpha is greater than or equal to 1/2, then with probability 1, the Brownian motion is not alpha Holder continuous. So we allow mu naught can be any Borel probability measure. It doesn't have to have finite support, doesn't have to be symmetric, and it can even have atoms at the edge of the support. But if one wants stronger regularity of R, you need to assume, at least initially, that the measure mu naught has density or doesn't have atoms at the edge of its support. All right, so that has to do with the hydrodynamic limit. Taking n to infinity, you get a free boundary problem. Now let's think about the large time limit for the free boundary problem. Okay. Naturally, if you take t to infinity, you would expect the solution to converge to a stationary solution, right? And so a time-dependent solution to this equation would be an eigenfunction of the Laplacian. Okay? So let's let R infinity be the unique real number, positive number, so that the principal Dirichlet eigenvalue of minus Laplacian is just 1. Okay? So there's a unique value of R for which this problem has a solution unique up to multiplicative factor. Okay. For that value of R, R infinity, and with U bar normalized to have total mass 1, we can prove that the solution to the free boundary problem converges uniformly to U bar, and the error is of order 1 over t. And the boundary function R of t converges to R infinity as time goes to infinity, like 1 over t. So for one dimension, R infinity is explicit. It's pi over 2, and U bar is a multiple of cosine. In dimension 2 or more, R infinity and the U bar can be computed in terms of special functions. All right, so let's go back to the particle system. For finite n, we're talking about a process in RD, and the distribution of the configuration at time t is a probability distribution on RD to the n. So our first result in this direction is that this process is positive Harris recurrent and has a unique stationary distribution, pi n, and the distribution of x of t converges exponentially fast to this stationary distribution, pi n. So that's for fixed n. Now think about the behavior of this stationary distribution as n goes to infinity. We can prove that as n goes to infinity, pi n converges in a sense to mu bar. That is, the density of particles in RD under this stationary distribution converges to mu bar, which is the solution to this eigenvalue problem. Okay. So here's how we state that more precisely. So given a configuration x, so this is a configuration in RD to the n, we let mu x be its empirical measure. This is a measure on RD, which is determined completely by the configuration x. So consider the behavior of this empirical measure under probability measure pi n on rd to the n. So what we show is that under that probability measure, the empirical measure, mu x, converges weakly to u bar in this sense. For any epsilon, for any Borel set A, the mass of particles in A minus the mass of u bar in A is small. The probability that that is larger than epsilon goes to 0 as n goes to infinity. Okay? And similarly, under this measure, the probability that the maximum differs from R infinity more than epsilon goes to 0. Okay? So that last statement has to do with this this lower part of the diagram. Think of the stationary measure as the large time limit, and as n goes to infinity, there's a sense in which the stationary measure converges to the large time limit for the free boundary problem. So the diagram commutes. All right, let me say a little bit about the free boundary problem. So let's suppose that the function u is actually C2 at the boundary. And just integration by parts, integrate the equation and use the mass constraint, you see that the flux through the boundary has to be constant. Right? Flux is -1. Again, that has to do with conservation of mass, but you also have source. So to offset the source, you have to have constant flux. Moreover, you can derive a formula for the normal velocity of the free boundary, which is the same all the way around the sphere. The derivative of r is equal to the integral of the Laplacian of u over the free boundary. So the boundary velocity depends in a non-local way on the Laplacian. Again, u is not necessarily spherically symmetric, so this Laplacian is not the same around the boundary. So this has some similarities to a problem of Caffarelli and Vasquez study in 92. This comes from a model for flame propagation. They look at the heat equation in a domain omega t. Inside the domain, it's assumed that u is positive and continuous up to the boundary, so it's equal to 0 on the boundary. And the nonlinear aspect comes from the constraint that the gradient at the boundary has magnitude c, where c is some fixed number all along the boundary. So they prescribe the gradient pointwise. And as a consequence of this speed of the boundary in the normal direction is proportional to the Laplacian pointwise. Okay, so in the same way here, the speed of the boundary is related to the Laplacian, but in our case, it's different in that we have this non-local dependence on the Laplacian. Another difference is that in their case, the solution disappears in finite time, whereas in our case, we have the solution exists for all time and has positive mass equal to 1 for all time. In their case, there's no mass conservation. So we find it convenient to use to relate this problem to a parabolic obstacle problem. It's useful analysis of a PDE, but also has some use at the level of the interacting particle system. So this is another free boundary problem, which is obtained just by integrating the function u over Euclidean balls. So f, the function of t and r. So this is the radial distribution function of the probability measure u. So I'm integrating over ball overall x having magnitude less than r. So clearly this, since u has mass 1, clearly this f is not negative. It's bounded by 1 everywhere. And in the region where f is less than 1, f has to satisfy this PDE. Moreover, because u is continuous and vanishes at the boundary, the derivative of f with respect to r is continuous. So the free boundary, the R, doesn't appear explicitly in this obstacle problem for F, but R is the boundary of the contact set for F. It's the boundary of the region where F is equal to 1. Right? So here, this is a representation of U. We obtain F by integrating over the ball of radius R. And so I'm calculating the mass up to radius R, and then that's F of R. So F is a function of R, is non-decreasing, and increases toward 1, the total mass. And the boundary of this contact set is the radius at which in which the mass of U is contained. Right? All right, so the general strategy for proving well-posedness of the original free boundary problem is to first look at the obstacle problem. We prove well-posedness for the obstacle problem with initial condition being just the radial distribution function for this probability measure mu naught. And this defines R of t, which is the boundary of the contact set for F. We prove that R is continuous for any positive time. So that determines R. So now given R, we go back and ask, can we solve the original free boundary problem in RD? So now we have an R, and we try to solve this problem. The tricky aspect here is making sure that the initial condition and the boundary condition and the constraint is satisfied. Right? So we propose an ansatz. The function U is, you think of this as a push forward of the initial measure by a density, a transition density, rho r, where given r, rho r is the density of Brownian motion that avoids the boundary before time t. So if you were to take fix x here, if you were to integrate rho with respect to the y variable, you would get the probability that the Brownian motion starting at x is in the set A and has avoided the boundary for time between 0 and t. Okay? So some mass is lost at the boundary. That mass is recovered by this factor e to the t. Right? So of course, for any function r, you could define these objects and write down this function, and it will solve the heat equation, but the mass may not be preserved. The point is that we're choosing a special R so that in fact the mass is 1 and the solution is continuous up to the boundary. There's some subtlety in the definition here. Notice how I'm excluding s equals 0 when I say avoiding the boundary. That's because we want to allow for the case that mu naught can put mass at the edge of its support initially. So possibly the Euclidean norm of x is equal to R0, but R moves away fast enough so that for any positive time, Brownian motion may avoid hitting the boundary. And that is, mass is not instantaneously eliminated. All right, so we proved that in fact this function satisfies all the conditions. All right. You could think of approximating a solution to the free boundary problem through a penalization, solving a linear problem on the whole line and then adding a nonlinear penalization, which is similar to adding a penalization term in the original PDE on RD, this absorption term. And this term is non-local, nonlinear, and basically it penalizes mass, which is beyond the radius at which the mass of U is equal to 1, right? But it's negligible. It's negligible inside the radius at which the mass is less than 1. All right, so the obstacle problem is useful because it provides a certain monotonicity that is helpful analytically for the study of the PDE, but it also has an analog at the level of the stochastic process. Let me explain that. So we're looking at the radial distribution function of U, and this satisfies the obstacle problem here. This problem has a maximum principal, and Let us think for a moment about approximating solution through operator splitting. Suppose we know the solution at time t, and we want to compute the solution at time t plus delta. Okay, so we're moving forward in time by delta. You could get an upper bound in the following way. First, take the function f at time t, evolve it according to the linear problem. Here, g delta, is the semigroup or Green's function associated with the linear part of the equation. E to the delta just comes from the growth over time delta. So this convolution here and multiplication by E delta just means we're evolving the function forward by the linear part on the whole line. Okay? And then we apply this cutting operator to enforce the constraint that f is less than or equal to 1. So the cutting operator is a nonlinear operator. It just cuts a function, Cm cuts it to mass level m, just by taking the minimum of the function in m. Right? So first evolve by linear equation for a short time, then cut and repeat. Okay? So you can check that gives an upper bound on f at time t plus delta. A lower bound may be obtained by reversing the order. First, you cut mass initially to a level e to the minus delta, so that less than 1, and then you evolve according to the linear evolution on the whole line to time delta, which allows total mass to be recovered, so that's still less than 1. And this provides a lower bound. Okay? All right, there's something similar to that. It happens at the level of the particle system, which is useful in proving the hydrodynamic limit. Here we're comparing the solution to the obstacle problem, nonlinear problem, to a linear evolution and this cutting procedure. At the level of the particle system, one can compare the NBBM, that is with the constraint, playing the role of the nonlinearity, compare that to an unconstrained branching Brownian motion. Okay? I'll use x superscript n to refer to the NBBM with the constraint, x plus the unconstrained branching Brownian motion. What you can show is that if you label the particles by their rank, their fitness, then there's a stochastic ordering. The ranks of the NBBM process stochastically dominate those of the regular unconstrained BBM. Or in other words, the cumulative distribution function for the unconstrained BBM stochastically dominates the cumulative distribution function for the NBBM. Okay, so that's a stochastic analog of this upper bound here, where we first evolve according to the linear equation, which is related to unconstrained BBM, and then cut, and that gives an upper bound for f. Okay. There's a similar lower bound where you start with the same initial condition, except for the NBBM, you first remove particles. I'm sorry, for the unconstrained branching Brownian motion, you remove particles that have the highest ranks, and then you can show that the unconstrained BBM stochastically dominates the ranks of the NBBM, or in other words, you get a lower bound. The cumulative distribution function for the NBBM stochastically dominates that of the regular branching Brownian motion, at least up until the stopping time at which the number of particles in the unconstrained BBM is less than n, is equal to n. Okay, so this is the stochastic analog of this comparison that happens for the obstacle problem. Okay, so a version of this coupling was used by Damasi, Ferrari, Prasuti, Sopranolotto in their study of the one-dimensional problem. Okay, let me just mention some more general aspects of this problem. So this Brownian-Bees model is a particular case of this more general NBBM process where you have a fitness function V. For a general fitness function V, say continuous, smooth, you expect that there's a hydrodynamic limit described as follows. The function U, the limit function to which the empirical measure converges, would solve a free boundary problem in a domain omega, which is a super level set of the fitness function. So omega sub L is the set of all points where V is larger than L. Maybe these are compact sets, maybe not. Maybe they're connected, maybe not. L of t is playing the role of RT in the Brownian B's example because it parameterizes these level sets. So the PDE holds in this family of sets omega L of t on the boundary U is equal to 0 and the total mass constraint is satisfied. So the boundary of omega LT is replacing, this is a level set of the function V, and LT is the fitness level at which selection is happening. So the interesting thing about the more general problem is that as time goes on, the topology of these level sets may change because, well, depending on the structure of V. So that makes it difficult to analyze. But we're thinking about this more general case now. So let's look at some one-dimensional aspects of this issue. Namely, when you have a fitness function that's not monotone and that the level sets may change topology. So this involves work with Aaron Beckman, who is now at Concordia. So here we're looking at one space dimension, but with a non-monotone fitness function. And suppose V has the form X plus a periodic function psi, and the oscillation in psi is large enough so that V is non-monotone. So an interesting feature of this fitness function is that, for particles to move to regions of higher fitness, they have to pass through a local fitness valley, right? So in this configuration here, you have some particles in one well, some particles in another, and the selection may happen on the left, but it could also happen at these intermediate places. So what happens? Well, it turns out you can observe behavior that's kind of like a pulse traveling wave. Here I'm highlighting in green the regions where the fitness function V has local maxima, and in gray, regions where the fitness function has local, well, didn't draw it very well, but local minima. The particles have to pass through these local minima in order to get to higher fitness. Right? So what you find is that particles for fixed n, they may move like a kind of pulse traveling wave. They can get stuck in a well for a little while, then eventually some particle wanders over to another well. Meanwhile, the particles in the back are selected, and this process continues. So Aaron proved this as it proved that for fixed n, there's a unique stationary distribution within a moving frame, that is the frame centered at the minimal particle or maximal particle. Moreover, there's a speed that is well defined. For each n, there's a deterministic constant such that the speed of particles converges to c almost surely in an L1. So she also observed a kind of metastable behavior depending upon the depth of these wells. Namely, if you can find intervals which are larger than pi in one dimension, this is the critical size of an interval where you have stationary solutions to the free boundary problem. If that's the case, then when n is large, solutions may get stuck for a long time because there's at least in the n to infinity limit, there's a stationary solution. So the particles can get stuck and exhibit a kind of metastable behavior before one of them escapes, and so on. An open issue is whether C is positive. Is it true that if V increases to infinity, does the ensemble go off to infinity? All right, so I'll stop there. A lot of interesting issues to explore. In particular, what aspects of this extend to the case of general fitness, especially when topology of V changes as the level sets change. I'm sorry, the topology of the level sets change. What's the effect of V on the population? Are there traveling waves? How can we understand this metastable behavior and the rate of adaptation? Is there a strong selection principle? That's this phenomena where the large N and large T limits commute. And one can consider interesting variants of this on graphs, so processes that random walks on graphs with a certain fitness landscape. All right, so you can find out more. We have a preprint on arXiv now. This one pertains to the PDE results. We have another one which should be posted with the probability results within a week or so. Thank you.